Hi everyone, I'm April Wang, a PhD student from University of Michigan. Today I'm presenting my research work on redesigning notebooks for better collaboration. First, let me introduce myself and my team. I'm a PhD student from School of Information, University of Michigan. My broader research area is human-computer interaction, with a focus on enabling and encouraging collaborations for exploratory programming. I'm advised by Professor Steve Oney and Professor Chris Brooks. In particular, I'm a member of the SPOT Lab, where we focus on understanding the factors that make programming tools usable and designing new tools for programmers. I'm also a member of the Educational Technology Collective Lab, where we explore intersections of technology with teaching, learning, and education, with a particular focus on learning analytics, educational data mining, and collaborative engagement. My work draws upon human-centered design techniques to explore barriers in different aspects of collaboration practices, and opportunities in redesigning the state-of-the-art tools to support collaboration. Today, I'm presenting two of our recent work along that thread. The first work is an exploratory study on how data scientists use computational notebooks for real-time collaboration. Computational notebooks allow data scientists to create computational narratives. This image shows Jupyter Notebook, the most widely used notebook platform. Recently, tools like Google Colab have demonstrated the possibility for synchronous editing. Multiple users are able to edit the same notebook while changes are updated in real time. This may bring new collaboration practices for data scientists. However, synchronous editing comes with its own challenges and may not always improve work efficiency. Studies have identified several issues with synchronous editing in other contexts, such as collaborative writing and programming. For example, in a synchronous code editor, things may become more complicated, while one person's compilation error may completely block others' work. Data science doesn't just involve the form of writing and coding. It also includes the reasoning process to extract insights from data. Thus, we believe that there can be unique challenges and opportunities for synchronous editing in the context of collaborative data science. In particular, we explore the following research questions. What tools and strategies do data scientists currently use for collaboration? Compared to working on individual notebooks in a collaborative setting, how does synchronous notebook editing change the way data scientists collaborate in computational notebooks? What challenges, if any, do data scientists perceive in synchronous notebook editing? To understand the tools and strategies data scientists currently use in practice, we first conducted a survey to ask their previous experience with collaboration. Our high-level takeaway from the survey is that synchronous notebook editing tools are relatively new and not widely used among data scientists. Most data scientists work in the traditional collaboration setting, where team members work on individual Jupyter Notebook and update each other's work asynchronously. To further compare how their collaboration styles varied between different approaches, we conducted an observational study with 24 data scientists working in pairs to solve a predictive modeling problem. We assigned groups to work in either the shared condition or non-shared condition. In the non-shared condition, participants worked on individual notebooks. In the shared condition, a Jupyter extension was enabled on the server to support synchronous editing in notebooks. The extension shares notebook edits and actions in real time. It executes code on a single interpreter and updates the output and runtime variables among collaborators. On a high level, we discovered 4 collaboration styles and aligned it with an existing framework of collaborative writing. Groups in the shared condition used single authoring, pair authoring, and divide and conquer style. Groups in the non-shared condition used the divide and conquer and competitive authoring style. Next, we looked at how participants communicated with each other. Participants in the non-shared condition relied more on Slack to send files, code snippets, and output, while participants in the shared condition are less distracted by those low-level coordinations and have more time to focus on more important issues. This indicates that working in a shared notebook may reduce communication cost by establishing a shared context. This relates to our analysis of the final submission. We looked at the error scores of each submission, the number of alternative models participants have explored, and the lines of content in the notebook. The result suggests that working in a shared notebook encourages groups to explore more solutions and leads to a better result. To summarize, our main findings indicate that synchronous editing helps data scientists maintain a shared understanding while reducing communication costs. It also provides the flexibility to branch through tasks. Thus, synchronous editing in Notebook improves the overall efficiency of collaboration. Despite all the benefits that collaborative editing features offer with respect to sharing context and improving productivity, we discovered several challenges in using the collaborative notebook. Let's take a look at an example. When working on individual notebooks and not clear about the plan, Bob and Alice both go ahead and explore the task on their own, even if they end up duplicating each other's work. While working on the same notebook, Bob is unlikely to duplicate the work if knowing that Alice is already working on it. Without splitting the task well, Bob may not know what to do until Alice finishes her part. They may end up with Alice doing 80% of the work and Bob doing 20% of the work. Besides the example we just discussed, our paper summarizes 6 challenges of synchronous editing in notebooks. For example, working on synchronous notebooks is more likely to lead to unbalanced participation, where one team member does the majority of implementations and ideations. In summary, our exploratory study investigates how synchronous editing in computational notebooks changes the way data scientists work together compared to working on individual notebooks. Working on synchronous notebooks improves collaboration, but also introduces new problems. The challenges in using the current real-time collaboration features suggest that we need better collaborative editing features for computational notebooks. In the next project, we aim to address one of the specific challenges discovered in previous study: improve explainability of the collaborative notebooks. When teams of data scientists collaborate on computational notebooks, their discussions often contain valuable insights into their design decisions. These decisions not only explain analysis in the current notebook, but also alternative paths, which are often poorly documented. However, these discussions are long and disconnected from the notebooks for which they could provide valuable context. For example, there is a relevant message saying there is a bug in the second cell, but we didn't know what the second cell was by the time that the message was sent. Team members typically need to have a shared context to make sense of the discussion. This can be particularly challenging as the notebook evolves. In this project, we propose to improve collaborative data science by connecting discussions with computational notebooks. To better understand how discussions can be useful for explaining the data exploration process, we analyzed the 760 chat messages collected from 3 data science group projects. We coded messages based on their purpose, their relationship to the evolving notebook, and the specific aspect of the notebook they mention. In summary, we derive 3 design implications from our findings. Chat messages are useful for explaining the exploration process, but they're difficult to follow. Notebook elements are frequently referred to in chat messages. Based on the findings, we designed Callisto, a plugin for Jupyter Notebook. Callisto augments Jupyter with several collaborative features. First, it allows users to share notebooks, collaborate in real time, and discuss with collaborators. Callisto adds a share button that generates a unique URL for collaborators to join the shared notebook session. Users can see a panel listing all the collaborators. Callisto synchronizes edits, runtime variables, outputs, annotations, and cursors among collaborators. Jupyter doesn't have built-in messaging features. To capture discussions, Callisto embeds a synchronous chat panel directly in the shared notebook. On the left side, Callisto includes a panel showing users' edits histories to provide awareness of collaborators' activities. After introducing the basic collaboration features of Callisto, let's take a look at how Callisto captures the connection between messages and notebook content. First, users can make direct reference to notebook elements in their chat messages by clicking the magic wand and then selecting the relevant notebook elements. Callisto enables 5 types of references: code references, cell references, annotation references, snapshot references which point to a previous notebook version, and the diff references which point to a comparison between 2 history versions. Now that we're able to capture the connections through explicit references created by users, what about other messages that do not have explicit references? When users send a message, it is likely to be relevant to the currently selected cell. Thus, Callisto automatically attaches a cell reference to the currently selected cell if users do not add an explicit reference. Users can also manually correct errors from automatic references. Now that we have created connections between messages and notebook content, how can we use this connection? Callisto enables 2 broad uses of these connections: to understand the context of a given message, or to find the part of the discussion that is relevant to a specific part of the notebook. The connection from messages to notebook content demonstrates what changes were made. When a user clicks on the reference, Callisto highlights the relevant elements in the notebook. Similarly, when a user clicks on the message, Callisto highlights the relevant cell in current notebook. Messages might become out of date if they reference an element of the notebook that is later modified or deleted. Callisto allows users to view the snapshot of the notebook when the message was sent. In some cases, users may want to understand what collaborators were doing between messages. When selecting 2 messages, Callisto can navigate users to the diff view, comparing 2 snapshots. In diff view, code differences and output differences are highlighted. For the other way around, the connection from notebook content to messages explains why changes were made. Callisto allows users to see which parts of the discussion are relevant for a particular part of the notebook. Users can enable the filter mode to only see messages and edits relevant to the selected cell. To assess how Callisto assists new collaborators when joining the collaborative notebook, we designed a 2-stage evaluation study. We first observed the participants working in pairs on a data science task in real time to test Callisto's usability. We then conducted a comparison study with the third individual joining the shared project using Callisto or a light version of the system with no contextual links. In stage 1, we observed that participants are hesitant to make accurate and polished references. On average, each group created around 7 messages that contain references, out of 100 messages, and most of them are the default cell pointers. With most connections are made by automatically inferred references, we manually went through the references and find that 92% are connected to the correct context. In stage 2, we evaluated how a new collaborator followed up with an ongoing collaborative project. We asked participants to first explore the notebook and answer 5 questions related to prior analysis. Then we asked them to use the tool in depth to follow up on the ongoing project. We compared the 2 versions of Callisto in this stage, the full version and the light version where we replace manual references with a textual description. We find that participants in the experiment condition understood the ongoing collaboration process better. Participants in both conditions reported a need to check the chat messages even though the notebook already contains some code comments and explanatory text. Comparatively, participants in the control condition have trouble following the chat message. Participants in the experiment condition benefit from an established connection between messages and notebook. Most of them kept the filtering mode enabled and went back and forth to check the context of messages. They also used the diff view to better understand how a code change resulted in an output change. For example, participants in the experiment condition were more aware of the relevant message. The result looks much better that are connected to this cell. Some participants selected this message and the previous message to generate a diff view. They were able to see that prior collaborators applied a log transformation, which made the distribution plot look less skewed. In summary, our paper contributes the design of Callisto with a set of features to make chat messages more useful for understanding the past exploration process in the notebook. Our evaluation provides evidence that creating mappings between messages, notebook elements, and versions helps data scientists understand and follow up on the exploration pipeline. Along this line, I would like to introduce some ideas for future work. The 2 studies I presented focused on professional data scientists. What's missing here is that many roles who are not skilled as data scientists collaborate with professional data scientists. We hope to investigate the communication challenges between data scientists and other stakeholders. Furthermore, we would like to explore approaches towards automatic refactoring computational narratives. Let me give you an example. This example shows 3 different levels of explanations for the code cell. The first one explains the process. We drew a distribution plot. The second one explains the results. The cell prices are right-skewed. And the third one explains the reasoning. The sale prices are right-skewed. This was expected as few people can afford very expensive houses. We hope to explore how code summarization techniques can be used to generate different levels of explanations. With that, I would like to end my presentation and open for questions. Thank you for listening.